Next, we consider what happens when a star has got to the point where it can't burn its next nuclear fuel in its core. So for low mass stars, it's got to the point where it's got a carbon or oxygen core. For high mass stars, it's got an iron core. At that point, it has no mechanism to burn that next nuclear fuel. What happens? So let's think about the low mass star first, and then we'll talk about the high mass star. So for a low mass star, we can look at its evolutionary track here on the diagram. So it's gone through its giant phase, gone planetary nebula, all of that stuff that we talked about earlier. And now it can't burn the next nuclear fuel. So what happens from this point is there's nothing to push back against gravity. So the star begins to contract in size. Keep in mind hydrostatic equilibrium at all times. So in order for the star to balance itself, there needs to be an internal pressure to push back. But there's not in this case. There's not a pressure that can push back. So it's going to keep contracting. That means pushing the outer layers of the star inside and getting smaller and smaller and smaller. Now what low mass means is a star that's less than 1.4 times the mass of the sun. Keep in mind that number. Remember that number, 1.4 times the mass of the sun. It will become important later on. So after it's gone through its planetary nebula phase, if there is less than 1.4 mass times the mass of the sun left, then it will follow this trajectory. The star will keep contracting down. But it doesn't contract forever. Instead, what will happen is that the electrons, which are negatively charged, don't like to be too close together. They'll begin to push back. So it's not going to be a fusion process that takes place. It'll be the electrons themselves that don't want to be pushed any closer together. And that's called electron degeneracy pressure. At this point, the star has contracted very, very far. It's now called a white dwarf star. So a white dwarf star is a star that's supported by electron degeneracy pressure. The electrons are too close together, and so they begin pushing back against the weight of all the star that's above it. Okay. Now these stars are small, but in that process they've also gotten very, very hot. So they're heating up as gravity is contracting things together. It's causing the star to heat up, but it's not becoming brighter. It's becoming dimmer. The size change is compensating for the heat raising. So it's getting hotter and dimmer over time, and that's why white dwarfs are found in this region of the diagram. They're very hot stars, but they're not very bright stars. Now, there is a white dwarf star in our night sky. I believe we've talked about this at some point earlier. I think when we talked about binary stars, Sirius A and Sirius B. So this is Sirius A and Sirius B in visible light. Sirius A is a bright main sequence star, and Sirius B is a white dwarf. And it's very dim in visible light. If you switch over to X-ray, though, you'll see that Sirius B is actually brighter than Sirius A in X-rays, and that indicates its temperature. It's a very, very hot, small object orbiting around Sirius A star. Okay. These white dwarfs are actually so small that they're only about the size of the Earth. So we've done some comparisons between the Earth and the Sun. Eventually, the Sun will actually be about the size of the Earth. Once it's gone through all of its red giant phase, planetary nebula, and is cooled down, shrunk down and heated up, it will be about the size of the Earth. Now, what is it made of? Well, at that point, all the hydrogen and helium will have been exhausted, and the carbon that couldn't be fused together will be left behind. So it's basically a giant ball of carbon. And that's what a diamond is. So you can think of a white dwarf as an Earth-sized diamond. Right. Now to illustrate this size difference and what's happening with the pressure, we have this diagram here. So the diagram here is representing atoms, and so there's nuclei and then the electrons. So in normal matter, the atoms are relatively far apart. They don't touch, right? They're not crunched together like people in a crowded room. They're sort of spread out, and they have plenty of room to move about. So there's an example here. A typical air molecule is about 68 nanometers apart from its nearest neighbor. So 68 nanometers sounds pretty small, but an air molecule is only about 0.4 nanometers. So its nearest neighbor is 170 times its own size. So think about your size is roughly 5 to 6 feet probably. Well, 170 times that distance is how far away the nearest neighbor is. So things are relatively empty. The atoms have plenty of place to fly around without interacting with other things, without bumping into one another. Well, for a white dwarf star, the atoms are compressed until the electrons are essentially right next to one another. And at that point, they're strong. That force between them is strong enough to push back. So they're going from 68 nanometers apart down to 0.4 nanometers apart. And so this diagram is sort of indicating what the atoms are looking like inside the white dwarf star. All the carbon atoms are crunched together, so they're almost touching. Now let's turn our attention over to the high mass stars, stars that are bigger than 1.4 times the mass of the sun. Now, as we talked about with those, they will have layers of heavier and heavier elements from hydrogen all the way up to iron, but they're still going to run out of fuel and collapse eventually. So when will that happen? Or what will be able to stop it from happening, that collapse from happening? It turns out that the stars that are that massive, the electron degeneracy pressure is not strong enough. And they're actually pushed inside of the nuclei of the atoms. And that creates an even more dense core. And because the electrons are pushed inside the nuclei, if you have a negative charge pushed inside of a positive charge, that makes it neutral. And so the core becomes entirely neutrons. And it's the neutrons pushing against one another now that can support the weight of the star. And so it's called neutron degeneracy pressure. However, in this case, the outer layers aren't really satisfied with this new equilibrium that's arisen. In fact, it's not really an equilibrium. And so something else is going to happen with those stars. But at least temporarily, we can think of that as the process, that it goes from sort of a layered onion with iron at the core, as shown in this diagram, and then collapses until all of the atoms are pushed to touch, and then the electrons are pushed inside of the nuclei. And then we have neutron degeneracy pressure at the center. Okay. So we can compare what happens with the white dwarf star to what happens to these higher mass stars. So let's think about this in relation to the sun. So if you took the sun and you compressed it down so its electrons are pushed back, it becomes the size of the Earth, as we talked about. Well, what happens if you push the electrons now inside of the nuclei until you get to this neutron degeneracy pressure? Well, it turns out that the size of the star goes from being the size of the Earth down to the size of a city. So if you take all of these electrons and you squish them inside of the nucleus, then you've taken away the electron cloud around the atom, and the nuclei will be touching, so it becomes a nuclear density. It's no longer made of atoms, it's just made out of neutrons. And those things are called neutron stars, and they're the size of a city. So we have the sun compressed down to the size of the Earth. A massive star, a high mass star, will be compressed down to the size of a city. So it's a little bit counterintuitive. The sun will eventually compress to a white dwarf the size of the Earth, but a higher mass star, a bigger star, will compress down to a smaller object, something the size of a city. Now, as I hinted at, that's not the end for these high mass stars. Something else is going to happen next, because this new equilibrium is not stable. And when the star collapses, it turns out that there's going to be an explosion that follows. So we will talk about that and what happens to high and low mass stars after they've gotten to these next stages, these death stages, in the next video.